everybody. We're going to talk today about some tools that are available to you on Unix specifically for developing software. This material is geared mainly towards people in the class who are going towards the next class in the sequence, heading towards 162. So specifically when you start going towards the transfer programs, you'll find that Portland State and a lot of the other institutions are requiring Unix. And that's a big part of the software development, and the tools that are available to you in the Unix environment are kind of the means of that. So we're going to take a look briefly at 4 separate tools that are available for developing your C++ programs in Unix. Let's take a look real quickly at just touch base and look at the difference between what we've just done, written bash scripts, and what the tools we're working with are made for. So this is the difference between scripted languages and compiled languages in general. With bash, we wrote a scripted language. So we have typically one file involved in our script. The contents, as we saw, were interpreted. So every time you run the script, each line is executed one at a time. And it is rather slow compared to compiled code. What does that mean? Well, we'll take a look at it. When we look at C++ codes and other compiled languages, typically our problem is stickier. We have more source code files to maintain. The code is translated into an executable file, so the actual hardware that it's running on, it plays more into the process of development than a scripted language, which is kind of just-in-time executed, versus a native solution like C++ compilers can generate. And again, you'll have a lot of files in a C++ project. If it's a file of any size that has a number of projects involved, you'll have a number of classes involved, and you have a lot to manage. And so some of the tools that we see, you'll see have a lot of sophisticated features just for dealing with the fact that you're having to manage a large number of files. So we've already been working with some C++ files, so you are familiar with the actual content, if not the meaning of these files and how the syntax operates and so forth. But we've been working with our search and replace features to practice using files called main.cpp, which is a C++ file, main.h, which is a header file frequently associated with CPP files, and also a file named makefile, which is a script to be run as part of the build system, the make system that we have, which we'll look at later. So we've worked with these. They should be familiar to you, and we'll be actually using these to develop a program, to compile a program. So if you have a copy of these handy, just grab a copy from my directory or send me a note and I will post them if you cannot find them. The tools that we'll be taking a look at are what I call the C++ tool chain, which simply refers to a number of tools that are available or that are used sort of in a sequence to produce the actual software product. So a tool chain refers to usually a number of tools that are available that are typically serve a particular purpose in a workflow. So here they are. G++ is the name of the first tool. That's the workhorse here, the compilation. It compiles source code into a binary executable. We'll look closer at that later. GDB is another tool that we'll take a look at. That is a debugger. Stands for GNU debugger, just like the G stands for GNU in the G++. So this is going to, the GDB program is going to expose debugging information in an executable that's been compiled with that debugging information, and will give you some ability to look into how your program is running at runtime and inspect variables and set breakpoints and so on. Another tool that we'll take a look at is called valgrind, which is a way for you to profile memory use of an executable that's running. With C++, the more you get into it, the more a error in your programming can lead to something called a memory leak, which is something of some concern when you're debugging. So this is a way to find that with valgrind. And then finally, we'll take a look at the make system, which is a utility for building executables and another way for you to organize the build process with a lot of nice little features. So we'll take a look at that too. So first, I'd like to talk just a little bit about the process of compilation, just in general. So it's different from other languages that you may see. a language like C++ or other compiled languages is different from the process that a Java program or a C# program goes through for the Java platform or the .NET platform. This typically is a native compilation, which will result in a executable file. So that's what I'm going to walk you through. So I have a kind of a weird mishmash of shapes over here trying to explain the compilation process here. We start with a source code file, which is a C++ file or an .h file in our case when we're going to be talking about compiling a C++ program. And that takes the compilation takes that as input. So when you run G++, it will use the files that you have your source code stored in, and it will generate object code. So object code is basically an intermediary format. It's containing machine code, however, it's not the complete compiled, assembled and linked version of the program. It is a number of object code files can be produced by this particular phase of compilation, and then it goes into a process called linking. Link will take that disparate collection of machine code living in object code files and will link them all together and produce usually one executable file, and that is the binary image, which is specific to the platform that it was compiled for. And when you run it, it will basically the image will be handed the control of the resources, and it will run in the same way that the script runs. However, this image is specific to the machine that it's running on, and it will run much faster, and it will actually replace the image and not invoke a shell. So here are some options I'd like to introduce you to for the first of our tool in our tool chain, the G++. Here's the syntax for running G++ with a few options that I'd like to call your attention to. So first thing you notice is that G++ is the name of the command. It's the actual character plus. It is a wrapper around a compiler called GCC, which is also going to be installed with this. Specifically, G++ configures the compiler to use the C++ language and not the C language, as GCC will do. So this is a wrapper around that, and when you run it, you're basically invoking the configured compiler with a couple of flags. And the first flag to note is the G flag. That's just a -G here as the first parameter. And this is saying I want my compiled executable image to have a set of symbols in it, which will give me information when I go to debug it. This is not information that is really critical for the program to run. However, if you're going to use a debugger, you might want to know the names of the variables and have some kind of look at the source code that it is being run in parallel with the actual execution of the machine code. So that gets you all of that. Using the G flag is going to say enable debugging information. The next parameter to pay attention to itself has a parameter, an argument, and that's the -std, indicates which C++ standard you are using. There are a number of standard releases of the language. It's happens at some interval here, and this is how you tell this compiler which one you want to interpret the source code as. So in this example, I'm saying use C++ 14 as the defining standard, and that's how I indicate that. I have the flag here, std, the equal sign, and then the name of the standard. And in this case, the valid values for that are 98, 11, and 14, and I expect that to change soon. Also, the O flag. Okay, so the O flag is what you want to name the output file. And be very, very careful. It is possible to make the mistake of indicating the name of the source file, particularly if you don't have a standard that you're following for naming. If you put your C++ code into something called main, and then you use the O flag like this one and indicate you want to call your binary executable main, it's possible you're going to overwrite your source code with the output, and that's a good way to lose your source code. So be aware of that. or just use extensions and follow the conventions like this. So in this convention, there is no extension. Notice there's no .exe. There's nothing to stop you from naming your files .exe on a Unix system when you produce a binary executable, but it is not part of the standard. It's not part of the standard in the operating system the way it is with Windows. So name it main, recommended if your program is named main. And then there's a list finally after all of the options. We start the actual list of the files that you include in your executable. So if you have a file that is referenced in one, you may need to include them in this list here. So more on that later. So let's take a quick look at what's in the files just so we can refresh what the code looks like. So let's take a look at the CPP file. Not a whole lot of code there. It's a very short program. Notice that it references in the first line, it has a hashtag include main.h. That has a similar function that the first line that we saw. It includes other files and allows the compiler to have a sort of a more control points over the compilation process. But it's not really the same thing as the hashtag, the shebang line that we saw in our shell scripts. But so you can see that this file, the CPP file, actually has a dependency on the .h, which might explain its presence in the list of files in our compilation. So that's what the CPP file looks like. Let's take a look at the .h file. Not much to it. And then if we take a look at the make file, we have some interesting syntax which we'll dive into later and take a look at. So now if I wanted to compile this with G++, I would simply use the syntax I just kind of showed on the previous slide. The G flag indicates I want debug information. I'm going to indicate the standard I want to use is C++ 14, and then I'm going to indicate my output file. I want my output file to be named main. If I don't name it anything, if I don't have an O, the name of the file that it generates with the binary executable will be called a.out. So if I don't want it to be called a.out, I use the O flag and I give it a name. And then I just type the name of the files I want to include in the compilation, which in this case are main.cpp and main.h. So I let that run. It very quietly produces no output, which is typically a good thing. If I had a bunch of errors, I might have some debugging work to do. So right now this compiled and it produced. Let's take a look. I have one new file, a main executable, and if I run that, it generates some output. It says hello world, and then it has information message about the program when it was compiled and so forth. So if I don't use any options, I get defaults and no debug information. So if I just do, and I'm going to try something. I would like to change the name of this to be so I'm going to leave the G flag off, and that'll produce a no debug main, and I'll run that, and let's see what we get. So I have two executables, main from the previous, that had the debug information, and if I would take a look at the file size, we see that there is a noticeable difference between the version on the first of the listing, main, and the file size of the no debug main that I just compiled. There's a significant file difference because there's no debug information in it. And then if I leave the output file name off completely, no debug, no options, no standard, and run that, and then I let that run, I get a.out executable, which contains the output, but also you can compare the file size and see that it also, the default for not having the G flag is that there's no debug information either. So That's what you get with the default, and that's a couple of options that you can use to set and compile your programs. So now that we have at least one executable with some debugging information in it, how do we use it? How do we see it? Well, that's where GDB comes in. GDB stands for the GNU Debugger. That's a tongue twister. Try to say that 3 times fast. So it basically, here's how it works. When you run the executable without a debugger, it just runs and it has a life cycle and then the process terms, and it's an event. Okay, so the debugger is software which also runs in its own process and attaches to your running program at runtime. So it actually is involved in starting up your program. So using GDB, as we'll see in a second, is a matter of starting the program and then also handing it the name of your program and letting it start and attach to the image that you have compiled with debug information. So that's how it works. And so that's kind of basically the limit of what we'll be talking about. What it does is it lets you see what's happening inside your program by doing things like setting breakpoints and inspecting variables and memory, and it's not something we're going to really need to do in this class. So that's kind of the point of demarcation, is it's just a debugger. So I'll do a quick demo because I want to show you the difference between running a debugger with debug symbols and running a debugger without debug symbols. But that's pretty much as important as this should be to you in your general Unix knowledge at this point, is what is a debugger, and how do you get the program through the pipeline, the workflow or the tool chain. So if we look at the man page, we see that it does a number of things. It helps you to see what is going on inside your program, or what was happening, or what it was doing when it crashed. So sort of a post-mortem of the runtime event as well. So take a look at the man page. Basically, its operation is... Oh, let me try a different server. So basically... Okay, so we're going to start with the parameter terminal user interface. This is one parameter, it's not 3. Don't go looking for a -t, you won't find it. Terminal user interface basically is saying run the debugger, but present a sort of a nice kind of a terminal based basic windowing area system. You'll see when we run it. So also we want to type the name of our program. So main is the name of the output, which has the debugging information in it. So let's see what this looks like if I run GDB in terminal user interface mode and hand it the name of my executable. Aha! So first thing it does is it takes over the screen and it shows a bit of splash screen information down here. So the area up here is configured right now to be displaying the source code. This was available in part of the executable file as a debug symbol, or a number of debug symbols. So this is where we can view that code. This is how we know where we are in the code, and this is basically a area in the window that we can enter commands. So it's now saying hit return to continue, and then we get a prompt. So that is the startup. So that's pretty much kind of the, like I said, the kind of the limit of how deep into debugging I want to go. I mean, you can read the documentation. Valgrind. So what is Valgrind? It's a memory profiler. What is a memory profiler? Good question. It is basically a reporting tool that gives you a picture or a profile on how your app is using the memory that it has allocated to it. So you can basically look for all kinds of problems, memory leaks, weird call return values. There's a lot of actual overlap between Valgrind and GDB. However, we introduce it as a memory profiler because GDB doesn't have anywhere near as nice as the profiling for memory that you can do in Valgrind. So we'll take a quick look at just running it. It's pretty simple. Like hang on here. Like GDB, you started using the you hand it the name of your binary that you want to profile. Let's see. Do I have a? Oops, I got to do some setup. You just basically, just like with GDB, hand it the name of your executable. And if you have parameters, you you hand it parameters too. So it runs. It basically displays a memory summary and gives any kind of information it can find on any memory which has been lost. That is allocated but not correctly deallocated. That is the basic output of Valgrind and the basic memory information that it will give you. So I'll leave you to read more about it if you want to learn more about it. But that's just basically the use of the tool. And so the last thing to talk about is make. The final tool that we'll talk about is make. So this is a little bit more involved, although not much more involved than the last three tools that we saw. Make is a utility, and it works in conjunction with the script contained in what's called a makefile. So I mentioned that it's a utility, and I threw in the word script, and then there's this thing called a makefile. So what exactly is make? Well, make is a program, and its utility and its purpose is to kind of manage a lot of source code files, and also the build process, the compilation process. So, as I mentioned, a lot of large projects have a lot of files in them, and as you saw, typing G++ plus the name of all of those files can get kind of tedious, especially if we're talking about hundreds. And then you have maybe different configurations. You might have a configuration to include some particular files for a test build or a development build. And you might want to use different files if you were to make a compilation for, say, a production build or a cloud build. So there's a number of scenarios that make and makefiles will support. There are other make systems. There's one called CMake that you may have encountered out there in the world. So they all basically are a scripting language, and they allow you to predefine configurations of builds so that the act of compiling is a lot easier and repeatable and error-free. Another thing that I wanted to point out is that it also has a nice efficiency emphasis, in that, you know, if it's a very large project, compilation can be expensive. So if you don't have to compile part of the program or look at a set of files because you know they haven't been changed since the last time an executable was built, the makefile allows you that optimization. So we'll take a look at that too. So the first thing to talk about, what is a makefile? I said it's a scripting language. Well, a makefile is the file that contains the script that you want make to run. And the default name is makefile. We've already seen a makefile. We've actually seen a very fancy makefile. But let's take a look at what a basic makefile looks like. So there's an example here in the right-hand column over here. And it has a very standard syntax. It's basically this. So there's a label. In this case, the label is all, and then there is a colon to indicate this is the end of the label, this is the start of the rest of the scripting syntax, and then you have a list of files on the first line. So when you put a label, you're basically saying this is the name I want to use to refer to this configuration of the code. So the first thing that will happen when it runs is it will make sure that the files on that first line, in this case main CPP and main.h, all exist. So it will check those when you try to run it, and then if they do exist, it will run the next line, which is just our regular old G++ line that we would type on the command line if we were to do this without a make system. So now all I have to do is type make, and by default it will look for this make file. If it finds one called make file, that's the one it will use, and it will look for by default all. I can have several labels in my file with different configurations of files and command lines to run. And so that would basically allow me to indicate with a parameter to make. I could say make all, or I could say make test build. If I had a test build label in my make file, it would find that and it would run that configuration. So it's pretty handy, and it sure saves you a lot of effort if you're going to have to type a lot of file names, or maybe change different parameters. I mean, if you have a testing environment where you want to maybe make sure that one target and output works, you can configure a number of different builds for test purposes as well. So that's the basics of the whys and wherefores and how you run a makefile. Let's take a look at the syntax. So you want to start with your label, as I indicated, and then a colon, and then you know, the sources are kind of conflicting about this. In the field, I've had students come back to me and say, you know, I don't actually need a tab here. And I've seen a lot of people say that, well, you actually do need a tab here. I think it's a version thing. I also think it might be an editor thing. I don't know. Just for the record, if it doesn't work without a tab, try putting a tab after that label and colon and see if that doesn't make it work. So enough about that. And then, as is indicated, the first line contains, after the label, the name of the files. And then, remember, it's going to check that these exist. And then on the next line is the actual command to run, which has my output, the name of my file, and the name of my input files as well. So on the second line, you have a tab character before all of that, and then the command line that I would normally type. So again, if you type make all, in this case, it will match this first line. It will verify that these files exist, and then it will run the second line. If they don't exist, it will not run the second line. So let's take a look at this working. So let's take a look at that. First of all, I would like to take a look at, okay, let me remove all of the executable files. Okay. Let's take a look at the makefile. Okay, so it's just as it was listed. Let's go zoom in here a little bit. So it's just as it was listed in the slide. I have the first line here, my label, followed by the colon, and then the tab, which is indenting, and I have the list of the files that I want to absolutely require to be in existence before building, and then I have my second line here, which is the debug information parameter, the standard of 14, and the output file name of main, and then the name main CPP. So there you go. So what happens when I have the make file existing in my folder, and I am in that folder as my working directory, and I type make, it finds the make file, it runs the make file, and then if I do a listing, I see that I have my output file is right there, and it's running. So the make file worked great, and that is basically a way to get a handle on configuring your build process. So I could also have typed make all, because I had that label all, and it would have found them. Either or, all is the default, so it will look for that by default if you don't give a label. So one final note, there is a nice feature that make provides, and that is back to that idea of efficiency and only compiling things that are needed. Now, if your label, which is, again, in the previous makefile it was all, in this example it's main, if the label matches the name of the output file that you've indicated in your build line, make will do something kind of nice. It will, before running the second line, in addition to checking that these files on the first line exist, It will also check the timestamp on these files, and it will only run if the files have been updated since the modified time of the executable. That is, have the source files changed since the last time main, the executable file, was built. So if they haven't changed and that condition isn't matched, it won't build. And so that's a nice way to skip things that don't need to compile. So you can have multiple lines, and if you skip things you don't need to you don't need to build, there's a gain. There's an optimization. So that's pretty much it. Those are the tools that I wanted to cover this evening, and hopefully you guys have found your way to the site by now. We're not going to do much more this week on this. I think I'm going to start throwing some extra credit up there and announcing it. So look for that, and if you are interested in or need to pick up additional points, that might be thrown out there. A couple of activities might be out there for you. So take a look. Also, I have another video that I'll be doing that is focused on kind of the Windows aspect of Linux. We haven't talked a whole lot about that. So that is pretty much it. I'm going to sign off. Thank you very much for your attention and time. Look for the second video. I don't know when it'll drop. I have to edit this one first and deal with some email. It's Monday. It's the 1st of June, and this is pretty much the home stretch. So hope you enjoyed this video. Take a look at the man pages and the material online for these tools. And if you are interested in learning more about C++, you can explore that as well. So have a good evening, and I will talk to you Wednesday.